the relationship here is essentially it's the same relationship that we had before, that we're approximating f of x with the tangent line, but now we're kind of rewriting that formula in a different way so that we're approximating the change in y by writing it as something that's approximated by f prime of a times delta x. So this is just a rewriting the tangent line equation. In an alternate form. So here, if I want to approximate the change in y for this function x to the 9th minus 2x plus 1, when x changes from 1.00 to 1.05. So the way we're going to interpret this is we want to approximate delta y, right? That's the change in y. It's really delta y, okay? By computing f prime of a. In this case, we're going from 1 to 1.05. So we'll use f prime of 1 times delta x. And what's delta x in this case? So remember, delta x would be the change in x. So it'll just be x going from 1.00 to x equals 1.05. So delta x would be subtracting. So we get delta x here would be 0.05. So that's what we'll do here is we'll take f prime of 1. So let's see, f prime of x is 9x to the 8th minus 2, using a derivative. And then f prime of 1 will be just 9 minus 2. 9 minus 2 is 7. So here the change in y is approximately 7 times 0.05. So I think that would be 0.35. Okay, so delta y is approximately 0.35. One way to interpret this is to think of delta x as a potential error. So what we've done here is we said, okay, if there's a small error in measuring x, like in this case, a small error of 0.05 in measuring x, then that propagates into the y variable by this amount here. So if I have an error of 0.05 in measuring x, then that would result in an error of 0.35 in the variable y. So that's another way that we can interpret this. So sometimes we'll see it worded that way, to think of delta x or delta y as an error in measuring that variable. So here's another example. Approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 meters to 3.9 meters. We know that the area, or the surface area of a hot air balloon is you know, a simple formula of the radius. So let's see, for a sphere, the surface area would be 4 pi r squared. So surface area formula for a sphere. Now, if I want to approximate the change in the surface area, well, we can do s prime of 4 in this case. And delta x would be actually delta r in this case. where delta r, notice here, our radius here, let's see, r, is changing from 4 to 3.9. Okay, so it's changing by a value of 3.9 minus 4. So I do final minus the initial, and here we get a negative value. So it'd be actually negative 0.1. The negative here is indicating is decreasing, right? So the negative change means it's decreasing. Here, let's compute s prime of 4 now. So s prime of r would be just taking the derivative with respect to r. So 8 pi r. So s prime of 4 would be 32 pi. So with that, the relative change, or the change in s, can be approximated with 32 pi times negative 0.1. So I guess negative 3.2 pi. And again, here it's negative because we expect this change to be decreasing, right? So here we see the surface area decreases by about let's see, what would that be? 3.2 pi is about 10.05. So, okay, so we see this actually pretty small change in the radius propagates to a pretty significant change in the surface area.
Professor, for the s prime r equals 8 pi r, why isn't it r squared?
So s is 4 pi r squared, right? So the derivative of r squared will be 2r. So this is just the derivative of r. So think of it like you're taking the derivative where r is the variable here, right? Like, does that make sense?
Yeah, thank you.
Okay, and one last thing that I want to mention here about this stuff is something called the, and I think that's the next thing we're going to look at, is, well, here's just a little summary of what we've done. The L of x formula here, f of a plus f prime of a times x minus a, is our linear approximation for our function. We use that to approximate f of x for values of x that are close to a. Or here's an alternate version of that we just did, right? Looking at how we can approximate a change in f or a change in y. So that's kind of what we were doing in the last two examples. And then what I want to point out here is that essentially what we're thinking of with this is now delta y over delta x. So delta y over delta x. We can think of as a way of approximating f prime of a when delta x is small. So maybe this kind of will lead nicely into what we're going to say with differentials, right? F prime is another way of saying dy over dx, right? So a differential is going to be looking at just the part dy or just the part dx, which is going to be related to f prime of a. So differentials, right? So let f be differentiable on an interval containing x. A small change in x is denoted by the differential dx. The corresponding change in f is approximated by the differential dy equal to f prime of x times dx. Okay, so these differentials are going to be notationally different than, say, the delta y or the delta x. But kind of thinking about how this is defined here, dy is equal to f prime of x dx, that's exactly how we approximated delta y. Okay, so that's why here we're saying delta y is approximated by dy. Okay, so it's just giving us now a particular notation for this f prime of x dx that is essentially going to be related, or a way of approximating our delta y. So so yeah, notationally it's a little different, but otherwise it's kind of the same thing that we were doing a moment ago. So let's see how this kind of relates to the picture. If I've got some change, small change in x delta x, same thing corresponds to dx. Then we can see dy and delta y kind of have the same relationship that it had before, right? Where this was our small change in y was delta y, and then this is the corresponding change in the tangent line. So we can see dy is a good approximation of delta y, and it gets better when we get closer to that point. So in other words, when delta x gets really small, then this is going to be a better approximation. So with that in mind, oh, I guess that was the last thing to mention. So with that in mind, we're going to we're going to think about here these differentials as we proceed into the next few sections. We're going to see this notation a little bit because it has something to do with this idea that we have a very small change in x corresponds to some very small change in y. And as we get, as x gets, or as delta x gets really, really small, then delta y is going to become closer and closer to dy. Okay, so we're going to think about how this notation relates to what we're going to be doing in the next chapter. Okay, but for now, when we're doing the differential, or sorry, when we're doing the linear approximations, we don't necessarily need to think about differentials so much yet, but it's an important notation that will become relevant later on. Okay, so let's see, do you guys have any questions about what we've done here with the linear approximation? Okay, well, our goal in the next section is to start to transition into what we're going to be focusing on in the next chapter, which is integration. So really, actually, the next section here is still part of chapter 4, but is helping us see how we can transition into thinking about integration without actually defining what integrals are explicitly, because here, what's going on in section 4.9 is we're focusing on the idea of antiderivatives. Okay, so this is a little bit trickier than taking a derivative. And I guess actually maybe a lot bit trickier in some cases. Because actually the rules for taking derivatives are pretty straightforward, right? We've got the product rule, we've got the quotient rule, we've got the chain rule, we've got all these rules, we've got the power rule, and so on. So we've got all these rules that help us just apply the rule and we get the derivative. For antiderivatives, now we're going to have to start to think in reverse. So our goal now will be to figure out, given some function, right? So if I'm given some lowercase f, my goal is to try and find an uppercase f such that the derivative of uppercase f equals to lowercase f. So here the idea is a reverse, a derivative in reverse. Right, so now, so it's like here, if I would give you an f of x here, we know that when we take the derivative, we get our f prime of x, right? So now we're trying to reverse it. Now I'm starting here. I'm given this part of it, or this equation, or this, I should say, this function, and we want to try and reverse it so we can get back to the original. So it's like now I'm given here f prime, and our goal is to try and find the original f. So that's what an antiderivative of. That's what an antiderivative is. It's the yeah, it's the function that came before the derivative. Okay, so we kind of have to start thinking about now reversing all the rules that we have so far. Some of them will be pretty straightforward, reversing the rule, simple formulas like the power rule or the trig functions will be easy sometimes. The tricky ones are going to be the ones where it's more complicated. For instance, I don't really have a straightforward reverse version of the power rule or the chain, or the product rule or the quotient rule or the chain rule. Those rules are much more complicated. And so trying to reverse them is going to be really tricky. So here, at least in this section, we'll start to just focus maybe on the simpler cases that are a little bit easier to reverse. So let's just take, for instance, these examples here. Like these ones are all easy, straightforward derivatives. Derivative of x is equal to 1. So let's think here, if I give you f of x equals 1, then the antiderivative, I'll denote uppercase f of x equals x is an antiderivative of f of x equals 1. Right, because here we see that the derivative of this uppercase f is equal to 1. Or here we know the derivative of x squared is 2x. So if I give you f of x equals 2x, then an antiderivative would be just x squared. I'm sorry, f of x equals 2x. Okay. Or here we have the derivative of sine x is cosine x. So then if I have f of x equals cosine x, then an antiderivative would be sine x. So here in thinking in reverse, we got to be a little bit careful though, because yeah, in this case, I kind of started with the derivative. So if I didn't have this to start with, then finding an antiderivative might be a little bit trickier. So let's think about that for a moment. One thing I should actually point out before we go any further is that really there's a whole family of antiderivatives. One thing I could have done here is, notice I say that f of x equals x is one antiderivative, but there could be many. For instance, I could add a constant here, say plus 2, for instance. And that plus 2 really actually goes away when I take the derivative, right? So the derivative of this uppercase f here would still equal to 1, right? So adding any constant here gives me the same derivative. So adding an extra constant there gives me the same derivative. So really here, in each of these cases, I could have plus just an arbitrary constant plus c plus c plus c. And it wouldn't make a difference, right? Because here, each of these cases, when I take the derivative of that constant, it gives me the same derivative. So yeah, in general, when we look at the family of antiderivatives, it's a way of representing all the possible antiderivatives. So when I write the family of antiderivatives for a particular f, we always put a plus c at the end. So that plus c will indicate that here we could add any constant to that antiderivative, and it still is an antiderivative. And you can kind of see why graphically that makes sense here. If I have, for instance, a line, you notice that any of these lines that I look at have the same exact slope. So all the derivatives of each of these functions are exactly the same. So shifting it up or down doesn't make a difference with what its derivative is. Same idea here, right? If I just shift this function up or down, then it doesn't make a difference in terms of what the derivative is. Remember, the derivative has only to do with the slope of the function. So each of these graphs has the same exact shape, just shifted up or down. So because of that, we know that the derivative of each of these functions is exactly the same. So just keep that in mind when we're finding an antiderivative. Generally, we're adding a plus c at the end to indicate that we're essentially writing all the possible antiderivatives that could occur, where c can be any constant. So we'll try and remember that when we're finding antiderivatives. So let's just practice with some simple examples. Suppose I want to find the antiderivatives for each of these. Notice the first one here is just 3x squared. Notice here we've got a 3 in front of it. We found an antiderivative of x earlier. Remember how we did that? Or actually we found an antiderivative of 2x was x squared. So now if I want to find an antiderivative for 3x squared, what you want to think about here is, again, try and think in reverse. What function, if I want to find an antiderivative here, what function has this as a derivative? Can you guys think of a function whose derivative is 3x squared?
Would it be x cubed?
Yeah, exactly, x cubed. So we know the derivative of x cubed is 3x squared. So therefore, the set of all antiderivatives will just be x cubed plus c. Right? And we can see here that when we take f prime, we get exactly that. So this is kind of like checking here, right? This one, maybe we can rewrite this one a little bit. Negative 9 over x to the 10. I can write this as negative 9x to the negative 10. Okay, maybe now it's a little bit easier to see what the antiderivative is here. So can you think here, what function?
X to the negative 9?
Very good, yeah. So what function has derivative negative 9x to the negative 10? Well, yeah, we can think backwards again here. The derivative of x to the negative 9 power would be negative 9x to the negative 10. Good, so then our antiderivative for this guy would be x to the negative 9. Okay, and just like before, we can just quickly check that when we do f prime, we get negative 9x to the negative 10, so that one works, right? And then looking at this last one here, we've got sine of t. So again, here we want to think what function.
Would that be negative cosine of t?
Yeah, very good. So remember, the derivative of cosine is actually negative sine. So if I want to get a positive here, then we're going to need a negative in front of cosine to make this a negative here. And actually, let me fix the variables. So we see that the derivative of negative cosine would really be negative sine. So it would be sine. Okay. So the antiderivative of sine t will be negative cosine t. Right, and again here you can just check that when I take f prime here, I get negative cosine t, which is negative sine t. So this is how we're thinking, right? Everything's in reverse now. So maybe the first thing that we can try and do is just think about what happened in each of these cases. Like when I was trying to find the antiderivative for 3x squared, well, notice that instead of reducing the power by 1 like we do when we take a derivative, we're actually going to increase the power by 1. Right? And then instead of multiplying by the power, we're going to divide by the new power. So it's kind of reversing that rule. So, oh, and actually here, but before I get to that, let's write the notation that we're going to use. So what we're calling indefinite integrals, these are just the notation for antiderivatives. Okay. So here, big F is an antiderivative of little f. Okay, so this is the integral notation. So when we're referring to indefinite integrals, it's just a way of denoting the antiderivative. Okay. So this will be the notation that we'll use to notate an antiderivative. Okay. And okay, you might be looking at the integral sign here is like this little, I don't know, this little curvy thing. And then this dx here is our differential, right? So for now, we can kind of just ignore this differential. It'll make more sense, I think, later on when we look at definite integrals, why we have this dx here. So for now, let's just assume this notation to just be what we're using to denote the antiderivative. So just as it denotes the antiderivative of f. Okay. And again, yeah, this notation will become a little bit more clear in the future why we have this differential dx here. But for now, we'll just kind of ignore that. That's just sort of indicating or telling us what variable we're dealing with. And looking here at one rule, notice here we're just reversing the power rule for the power rule the forward way, right? The power rule for derivatives, right? Remember, if I take the derivative of x to the p, it'll be px to the p minus 1. So this rule here reverses this rule. So the integral of x to the p, in other words, the antiderivative of x to the p is, instead of subtracting 1 from the power, we're going to add 1 to the power. And then instead of multiplying by the power, the original power, we're going to divide by the new power. Okay. And we can easily check here. Let's check that this is valid. In other words, let's make sure that when I take the derivative of the right-hand side of this equation, I get x to the p. Okay. So in other words, what we're doing is we're going to apply the power rule to this. So p plus 1 in the bottom is just a constant. So I'm just going to apply the derivative to p plus 1 here. So it'll be p plus 1 x to the p plus 1 minus 1, so x to the p. And now those p plus 1 cancel. And I just get x to the p. Okay, so we can kind of see how this works. If I've got the integral of x to the 5th, it will be x to the 6 over 6. Right, because I know now when I take the derivative, right, check to see that when you take the derivative, of x to the 6 over 6, yeah, we get 6 comes down. Those guys cancel. So we just get x to the 5th. Okay, so let's practice this rule a little bit. Oh, actually, here before I do that, let's get a couple of other rules out of the way. So these are pretty simple ones: the constant multiple rule and the sum rule. So these are actually just kind of borrowing some rules from derivative properties. We know that if we're taking the derivative of a function, then any constant multiple can be pulled aside. So the same can be done with an antiderivative. If I have c times f of x, then I can pull that c aside when I'm taking the antiderivative and just focus on taking the antiderivative of f of x and then multiply it by c. Or here, if I'm taking the antiderivative of a sum of two functions, f of x plus g of x, then we can just take the antiderivative of each one individually. Okay, so combining these rules together allow us to deal with polynomials. So let's just start with something simple like this. Suppose I want to find the antiderivative of 3x to the 5th plus 2 minus 5 times the square root of x. So according to those last two rules, the constant multiple rule and the sum rule, I can just evaluate each antiderivative for each term separately. And here we've got 3x to the 5th, so this will be 3 times the integral x to the 5th plus integral 2 and then minus 5 integral of x to the 1/2. I'll write it like that, because now we can apply the power rule there, or the antiderivative power rule. Okay. So for the first one here, it's just x to the 6 over 6, like we did a moment ago. This one, you notice, is kind of missing an x variable. But anytime we have a constant, we can remember that the antiderivative of a constant will be multiplied by the variable x. So here, for instance, we know that the derivative of 2x is 2. So the antiderivative of 2 will be 2x. Another way to view it is if you've got, so if I'm taking the integral of any constant, say 2 in this case, it's really like the integral of 2 times x to the 0. So when I add 1 to the power, I get x to the power of 1. So in fact, yeah, the power rule for antiderivatives here applies as well. But for me, it's easier just to remember if I have a constant, then that came from the derivative of that constant times x. So the antiderivative would just be 2x. And then here minus 5. Okay, so help me with this one. How am I going to get the antiderivative for x to the 1/2 power?
Would that be like, isn't it be the x to the power of 3/2 divided by 3/2?
Yeah, good, exactly. So, so maybe here, let's write it out. So it's x to the 1/2 power. So we're going to add 1 to the power, which will be 3/2, and then divide by that new power, right? So it'll be, yeah, x to the 3/2 over 3/2. Well, if we're dividing by 3/2, you can think of it like we're really multiplying by the reciprocal 2/3. So it'll be, yeah, x to the 2/3, x to the 3/2. Something like that. And then again, here, notice I'm putting a plus c at the very end. Okay, so just doing a little bit of simplifying. 3/6, that reduces to 1/2. Plus 2x minus, here this would be 10/3. X to the 3/2. Right, and if you want, you can check here. Remember, the way we check is you just take the derivative and see that you get the same thing that we were starting with here. So in other words, taking the derivative of our answer here should bring us back to the original integral. And we would see here that when we take the derivative of 1/2 x to the 6, we get 6 times 1/2 is 3, x to the 5th. Derivative of 2x is 2. And then here the derivative of minus 10/3 x to the 3/2. So that would actually, let's see, 3's would cancel. So you'd have 3/2 times 10/3, which would reduce to 30/6, which is 5, right? So minus 5x to the 1/2. And that's exactly what we started with, right? So let's try another one here. We've got the integral 4x to the power of 19 minus 5x to the negative 8 over x squared. Now, we don't want to deal with something that looks complicated like this. So we think of how we can simplify it into a form that allows us to use the rules that we have so far. In other words, if I can rewrite this as a sum or difference of power functions where it's just x to some power, then I can just integrate each term separately. So in this case, that's exactly what we'll do. We'll just, before we go any further, we'll divide each of these terms by x squared. So it's like 4x to the 19 divided by x squared can be simplified. 5x to the negative 8 divided by x squared, that can be simplified. X to the power of 19 divided by x squared will be x to the power of 17, right? And then let's see, x to the power of negative 8 divided by x squared. How does that one reduce?
The negative 10.
Good, you get
Yeah,
5x to the negative 10, right? Good. Now writing it like this, we can just integrate it with the power rule. All right, so it's just 4 integral of x to the 17 minus 5 integral of x to the negative 10. So again, here we'll add 1 to the power. So 17, we add 1 becomes 18. So we have x to the 18 over 18. Here we add 1 to negative 10, we get x to the
negative 9.
Negative 9, very good. And then divide by negative 9. And then plus c. And then finally here, let's simplify this a tiny bit. 4 over 18, I think that reduces to 2 over 9. And then here we got negative 5 and then divided by negative 9, so that becomes plus 5 over 9, x to the negative 9. Okay, so again here, the strategy was to try and simplify this first so that we can get it into a form that we can just integrate each term separately. That's using that sum rule. And let's do one other example here. Similarly to the last one here, I need to do something before I can integrate.
wouldn't you need a factor? Or I mean, distribute?
Right, because here you have a product of these two functions. So the way it's written here is very hard to find the antiderivative. So we'll just FOIL it out first. Okay, so I'll just distribute everything out. So let's see, we got z squared times 2z will be 2z cubed minus 5z squared plus 2z minus 5. Okay, now it's all spread out like this, so we can now integrate each term separately. Now we can do the sum rule, excuse me. Here I'm just kind of writing them out separately to remind you that we can do it this way. Just to kind of remind you that these are actually just all their own rules. So here we apply the sum and the constant multiple rule there to look at each term separately. Okay, so but really we're just going to integrate term by term. So integral of 2z cubed is, well, we add 1 to the power, so it becomes 2 times z to the 4th over 4. 5z squared, we'll add 1 to the power, so it becomes 5z to the power of 3 over 3. Two z when we add 1 to the power, so it's like a power of 1 now. So when we add 1, it becomes z squared over 2. And then the constant here, 5, when we integrate will be 5z. Okay. And then finally here, reducing some of these terms, like 2 over 4 reduces to 1/2. Minus 5 over 3 z cubed. Plus 2's cancel, so just z squared. Minus 5z. Okay. So at this point, we don't have a lot of rules to deal with integrals, to do antiderivatives. So the nice thing is, at least in these last few examples, these were all able to be written in this form where we can just apply the power rule, right? But we should also think about other kind of antiderivatives we can look out for, which are the antiderivatives of the trig functions. So let's think about those here with some quick examples. These ones are going to be, ones that you probably want to just memorize. So for instance, if I look at the integral of secant squared, I should immediately just think about, okay, well, do I already know a function whose derivative is secant squared? Can you guys think of a function whose derivative is secant squared?
Tan.
Tangent. Exactly. So we have this one pretty much memorized. If we memorize the formula for the derivative of tangent, which we know is secant squared, then we actually have an antiderivative formula there as well. So it's antiderivative of secant squared is tangent. Right. Okay, so there we have the antiderivative formula with barely any work, well, practically no work. Just remembering the derivative formula. So in fact, that's when you probably want to just remember, right? Here's another one, 2x. Well, we actually know that that's the derivative of x squared. Okay, so we got that one. And we know sine, when I take the derivative of sine, I get cosine. So antiderivative of cosine is sine. And again, here you can just double check. Remember that, yeah, the derivative of all that stuff will just be 2x plus 3 cosine x. Just check. And now the last one here is perhaps a little bit trickier. In fact, maybe looking at it, it's not entirely obvious what the antiderivative is. What would you guys suggest we do here? Does anything come to mind when you see something like this?
Convert cosine squared into cosecant squared.
Sine over.
I think it would be secant squared if you put it in the top.
You do sine over
Oh, sorry.
times 1 over cosine.
Sine over okay, so that's a little bit trickier, but where are you going with that?
So then you'll have tangent times cosecant.
Okay, and where are you going with that? So if I write sine over cosine is tangent, and then 1 over cosine is secant. So
I don't know.
I mean, you're
Can't
headed
you
in
just-
the right direction, and this is perhaps not an obvious thing, but now can you think of a function whose antiderivative or whose derivative is tangent secant, tangent x secant x? So again, this is one you should probably memorize, that we know that the derivative of secant is exactly that, right? Which we can check here, right? We know that the derivative of secant x is exactly that. Oh, sorry, there should be dx there. Plus c.
Was there a different way to do that, or was that good?
So yeah, I mean, there could be a different way to do it. So that's something to keep in mind, is there could be multiple ways to get the answer in the end. Although in this case, it might be tricky to think of another way that leads you straight to an obvious antiderivative. I mean, we're going to spend a lot of time just well, actually, I would say in general, finding antiderivatives is not a straightforward thing. And we're going to spend a lot of time over the next chapter just thinking about different ways we can manipulate our integral into a form that we can find an antiderivative for it. In fact, in Calculus 2, you'll have like a whole chapter dedicated to integration techniques. So techniques for getting antiderivatives. So yeah, if it's not something obvious like this, then I mean, if it's not in a form where it's obvious what the antiderivative is now, it's usually going to require some sort of manipulation like this. Because another thing you might guess, or you might think to do would be to maybe rewrite this using some other trig identities. Like cosine squared, that's 1 minus sine squared. But then, okay, well, what can I do with that? Well, maybe then you can try messing around with that some more and see where that leads. Or another way to approach it would be to later on we'll talk about this, but another way to approach it would be to try something called substitution. And we'll see that, in fact, actually substitution would be another way to get a result here. But it actually might lead you to an answer that looks a little bit different than what we got here, but is equivalent. Okay, so anyways, let me leave it there. I think we can pick this up again next time and just do some examples. So here's just a little overview of all the formulas for derivatives of all the trig functions. And therefore, each of these derivative formulas really corresponds to an antiderivative formula.